Okay, we are moving on to section 4 of chapter 2, something called the chain rule. All right. The chain rule is talking about if you have a composition of functions, so one function inside the other. And so instead of having just x squared, you have parenthesis x plus 2 parenthesis squared, where at that point we would normally have to FOIL it and then use our power rules to derive it. We don't have to FOIL it. We can just do the chain rule to derive it. So here's our composition. I always talk about things as inside and f being outside. So g would be the inside function, f would be the outside function. Okay. What that looks like is you are going to derive the outside first and then multiply it by the derivative of the inside. It's easiest on this definition here. If you look, it says take the derivative of f of g. So I'm going to keep my inside of g of x the same, but I'm just going to derive the outside. So it's f prime, still of just g of x, but then times g prime of x. Okay, and a lot of that's easier to understand through an example. So we'll do several examples. So we're going to find the derivative of y equals 1 over x plus 1. What I would do first is I would rewrite this as x plus 1 to the negative 1. Now, of course, we could do the quotient rule, but for the sake of practicing the chain rule, we're going to do the chain rule. So you could do low d high minus high d low over the square of what's below, or I could do the chain rule, which says that x plus 1 minus 1, or to the negative 1, if we're doing the derivative, I will derive the outside, which means I'll take my exponent and multiply it down in front, just like we normally do when it's just x. I keep my inside function exactly the same. I didn't change it. And because I'm deriving the outside, I still have to decrease the power by 1. So negative 1 minus 1 is now negative 2. Then I multiply by the derivative of the inside, and that is 1. I'm going to write it for the sake of practice. You don't have to write that. I will then simplify it. Okay. What has the negative exponent is the x plus 1. Excuse the bell, guys. And then the negative 1 doesn't have a negative exponent, so it'll stay on top. I've seen on some of your homeworks where you guys are messing up some of that algebra, so be careful. Only things with negative exponents go down, and it goes down below the term it's in. So if you're adding and subtracting, it doesn't go underneath the whole adding and subtracting. It goes underneath that single term. We'll try to find some examples like that. Okay, so then that would be, and if you did the quotient rule, you'd get the same thing. So then another practice of chain rule, there's no rewriting this one. It doesn't need to be rewritten. But if I do the derivative of y with respect to x, the derivative of my outside function is sine, my inside function is 2x. Okay, so the derivative of sine is just cosine. I'll keep the inside the same, times the derivative of the inside, which is just 2. And I should rewrite that as 2 cosine 2x. Okay, I would rewrite this one to be 3x squared minus x plus 1 to the 1/2 power, so that when I do my first derivative of y, I will do the chain rule. So I'll do the derivative of the outside, and I will keep the inside the same. But then I have to subtract, continue my derivative of the outside. My exponent will now be negative 1/2, because I subtracted 1 from 1/2. So then I'll need to simplify that. So my 1 is in the top. My 2 is still in the bottom, but now I have 3x squared minus x plus 1 in the denominator with a power of 1/2. Or you could rewrite that part as a square root of 3x squared minus x plus 1. Okay. This one might help to rewrite it because you have to remind yourself when it's tan squared of x, which means the same thing as tangent x, the entire thing being squared. So my inside function will be tangent x, and my outside function is the fact that it's squared. So if I do my first derivative of my y function, the 2 comes down in front, and that power decreases by 1, but the inside stays the same. Then I multiply by the derivative of tangent, and the derivative of tangent that you're going to have to memorize is secant squared. All right, and the only simplification, you don't have to write this 1 as an exponent. It doesn't hurt it if you leave it, and you can just leave it like that. There's not any simplification you can do. Keep in mind, your trig functions can't ever be empty, so make sure they always have a variable or a number inside of it. And the last one on this page, we'll do dy over dx. It's already simplified. If you were to do this with power rule, you would have to do x squared plus 1 times x squared plus 1 times x squared plus 1. Actually go and FOIL and distribute all that out. And then you would do the power rule where you just multiply the number in front and decrease the power. Chain rule actually saves us quite a bit of time, especially on problems like this, because I will multiply my power in front. And so there's the derivative of my outside, keeping my inside the same, times the derivative of the inside, which is just 2x. Simplifying that, multiplication is commutative, so I can rearrange it. So I'm going to multiply my 3 and my 2x to be 6x, and then x plus 1, or x squared plus 1, all squared. So we have that. Okay. All right, so we're going to change a little bit. We're going to find all points on the graph for which the first derivative of f is equal to 0, and those for which f prime of x does not exist. That got cut off. Okay. So if we're talking about points on a graph for which it's equal to 0, it's talking about having a horizontal tangent, so where the slope is 0. Okay, so we'll do our first derivative, and then where it doesn't exist, that would be where it has a vertical tangent. Okay, so if you're ever asked to find horizontal slopes or vertical slopes, it's talking about a horizontal slope has a 0 slope and a vertical slope has a non-existent slope. Okay, so first thing though we need is, either way, both are asking us to find f prime for both things. So we will do the first derivative of x. It may help to rewrite this, okay, as we have the x squared minus 1, but instead of the cube root of something squared, we can give it a power of 2/3. Okay, that is exactly the same thing. I've seen some of you do that on some of your assignments, and that's great. All right, so I will chain rule it. So derivative of the outside, keep the inside the same, times the derivative of the inside. I will simplify that a little bit for the sake of solving, so that I have 4x over 3 times x squared minus 1 to negative 1/3. Or actually, I should move that down below. So I'll have 4x all over 3. And if it helps you, it kind of helps me sometimes to solve it. I may write it like that. Okay, so we're trying to figure out two things: when it's equal to 0 and when it's undefined, essentially, where it doesn't exist. So fractions and quotients are equal to 0 when the numerator is equal to 0. So if I'm trying to figure out this, I'm actually only looking at this. Again, fractions are only 0 when the numerator is equal to 0, unless it makes the denominator equal to 0. So I'll divide both sides by 4, and I get x equals 0. So at x equals 0, the slope is 0. Okay, so we say f prime of x equals 0 at x equals 0. There's one of my answers. So then I need to figure out, where is f, or 4x over 3 cube root of x squared minus 1? When is that undefined or doesn't exist? So we're looking for the does not exist here. So fractions don't exist when there's certain rules they break. So for example, I can't have negatives in square roots. I can't have the bottom be 0. And so we have to figure out where it doesn't exist. It wants the exact values of where it doesn't exist. So exact values where it doesn't exist is, it doesn't exist where the denominator is 0, because cube roots are great. A square root or an even root, I can't have negative values inside of it. But a cube root or a fifth root or a seventh root, any odd root, that's fair game. You can have negatives. But the bottom can't be 0. So I need to figure out what makes the bottom equal to 0, because it's not supposed to be. So we need to solve this. So I can divide both sides by 3. Still can't be 0. And then I can cube both sides, and 0 cubed is still 0. And then this left side factors like this. And so then I can see then that x can't be negative 1 or positive 1. Okay, so we can say f prime of x does not exist at x equals negative 1 and 1. Okay, so that means it's going to have a vertical slope there and a horizontal slope at 0. If it had a square root or an even root, you'd have to do that a little differently. All right, next example. We're just finding the derivative, but we're making it a little more complicated. So there's now multiple rules. We're not just using chain rule. In this case, we're using product and chain rule. So I have my first function, or thing 1, and then I have my second function, my thing 2. So when we do our product rule, because it's x squared times that quantity, I can do 1d2 plus 2d1. It may help to rewrite this, or think of it as x squared times 1 minus x squared. Oops, I put that squared in the wrong place. Squared goes here to the power of 1/2. Okay, so then my f prime of x is equal to 1. My d2 I have to chain rule. So d2 is derivative of the outside, keeping the inside the same, times the derivative of the inside. Derivative of 1 is 0. Derivative of minus x squared is negative 2x. Okay, so that's my 1 d2 plus 2 d1. So I have this big thing right here. All right, let's go ahead and work out simplifying a little bit and negative exponents and all of that. So if you notice, if I combine my x's that are not with that negative exponent, I would have this x squared and this x. I am going to have an x cubed in my numerator. And then my numbers multiplied, I have a 1/2 and a negative 2, so I'm going to have negative x cubed. And then I will bring this down below so that it can have positive exponent. Okay, that negative exponent doesn't affect the term on the right because it doesn't have any negative exponent. So this is still just 2x 1 minus x squared to the 1/2. Okay, so then if you notice, I can actually simplify this more. If I were to actually add these, I need a common denominator. So the denominator of the term on the right is currently 1. So I need it to be 1 minus x squared. So what I'm going to do is I'm going to multiply top and bottom by 1 minus x squared to the 1/2, so that this denominator is now 1 minus x squared to the 1/2. Notice I simplified that. I'd get exactly where I was before because those would cancel to be 1. Okay, that is actually really helpful though, because now I have a common denominator. My denominator for both terms is 1 minus x squared to the 1/2. Okay, so then if I'm combining my top, I have my negative x cubed plus that term on the right. I have identical terms here being multiplied together. When you multiply things like that, you add those exponents. So I'm going to keep my 2x there, but I now have this to the first power, if you want to write it, because 1/2 plus 1/2 is that. So it still simplifies even more. I can distribute that 2x through so that I have 2x minus x cubed like this. And then I can, minus 2x all over 1 minus x squared to the 1/2. And I can combine like terms in the top, and I can have 2x minus 3x cubed, or negative 3x cubed plus 2x, there you're going to see it, all over 1 minus x squared. The only other thing you could do is you could factor an x out of the top, and that's about all you can do. It's not going to cancel with anything in the bottom, but it wouldn't be wrong if you had 2 parentheses x minus 3x. Nope. Factor an x, not 2. X parentheses 2 minus 3x squared. You could do that on the top and keeping the bottom the same. Okay. All right. You'll have to rewind that if you want to do that, because I need to erase a little bit because I ran into my space for my next problem. These problems are going to start taking up a lot more space. Okay. They get bigger and bigger. And then for a while, we'll get some short ones again. It kind of goes back and forth. Okay. So we have that answer. You may have to pause it and rewind it to go get it. All right. So then part B, if you notice, we now have a quotient, okay, which is great. But I'm going to have to do that quotient rule. So it might consider the bottom. Think of the bottom as x squared plus 4 to the 1/3. At some point, that might be easier when you're doing your derivative. All right, so I'm going to do, for my quotient rule, f prime of x is equal to low d high, which is just 1, minus high, d low, which I'm going to use that to the 1/3 power. It's easier to derive from there. Derivative of the outside, keep the inside the same. You have to subtract 1 from the exponent when you do the derivative of the outside, and then times the derivative of the inside, all over the square of what's below. And you can either write it as 2/3 exponent, or you can write it as root 3 squared. I'm going to do it as 2/3 for right now. We'll see if that's helpful eventually. Okay, it may not be, it might be, we just kind of see. All right, so then I need to simplify in my numerator so that cube root of x squared, let's see if I can squeeze it over here, it'll stay the same, but I've got a lot going on this other part. I've got a 1/3, a 2x, a negative x, and I have that negative exponent I'm going to have to take care of. So I still have the minus, and I'm going to end up with a fraction over here. My denominator is going to be that x squared plus 4 to the power of 2/3, now positive. And then my numerator has that negative I already have, and the 2, and then the x is being multiplied, so that I have this. It's negative 2x squared. Okay, is what I have now. All right, so denominator, though, of the whole thing is still x squared plus 4 2/3. You need to simplify it. So I need to actually combine the top because I don't want a fraction within a fraction. And so I'm going to need a common denominator. Well, the common denominator of the first term, denominator here is 1. So I'm going to multiply top and bottom of that term by the x squared plus 4 to the 2/3 power. Okay, so it might help you to consider rewriting. Give me a second, see if I can do this without messing it up. That, instead of writing it as a cube root, writing it as 1/3, because then if you notice, when I multiply top and bottom of that fraction on the left by x squared plus 4 to the 2/3, I'm going to add those exponents, making it 1. So when I get a common denominator, I multiply both top and bottom by x squared plus 4 to the 2/3 on top and on bottom, x squared plus 4 to the 2/3. When I say bottom, I mean that 1, not the entire bottom. I'm going to get just x squared plus 4 to the first power, all of it, so I don't need to write that 1 in parentheses, minus 2x squared. That thing is over x squared plus 4 to the 2/3, and then the whole thing is over x squared plus 4 to the 2/3. So something will happen there in a second. We'll go ahead and simplify the numerator so that we have 4 minus x squared, or negative x squared minus 4. That is kind of up to you. Let me make sure I'm not messing anything up. Okay. And then, I think that's right so far. Okay. And then our denominator is going to be, when I have this, think of a fraction and a fraction. So when you do that, you multiply by the reciprocal. So this fraction is currently this. When I multiply the reciprocal, I'm going to multiply those denominators. And I'm going to end up with x squared plus 4 to the 4/3 power, because I multiplied those denominators together. That happens every time. So if I have like 1/2 divided by 2, I'm going to have 1/4. If I have 1/2 divided by 3, I'm going to have 1/6, because you are every time going to end up multiplying those denominators, because you're going to multiply by the reciprocal. And so that's what happens every time that you do that. And I'm just double checking, make sure I haven't made any major mistakes here, because it is kind of a fragile problem when there's so much going on. And I found one place that I left something off on, but it should be easy to fix. If we were in person, you would probably have caught it for me. But this 1/3, I left it out, and so there should be a 3 there. Okay, making there a 3 there, meaning lots of things need to be multiplied by 3. So when I distribute, it should have been a 3 here and this be 12. And so we'll just kind of fix that error there so that I get 3x squared minus 2x is actually x squared. And then I have positive 12. Okay, sorry about that. So be careful with those little fractions because they're easy to miss, obviously. Okay, and then make sure you get that answer. That is out of your textbook too. If you guys ever go to the sections, these notes, I don't just make them up. I take them from your textbook, which is why they match up to your homework. Okay, let me erase a little bit so I can get some space. This next problem, it looks like a doozy, so we'll see if it is or not. Okay, so it's a chain rule of a quotient. So instead of, the last one was a quotient that had a chain rule in it, we're chain ruling this entire quotient. So if I'm going to do dy over dx, I'll do the derivative of the outside, keeping the inside the same. So that whole fraction, it actually gets to stay. And then my exponent will go down by 1. I'm not going to write the 1. And then I need to derive the inside, which means I have to do the quotient rule. So I'm going to do low. This is just the inside, so it is just this part, not with the squared. We already handled that. Low, d high, minus high, d low, derivative of the top, all over the square of what's below. So we have this big thing. It looks really crazy. What we do need to do is we need to simplify. So, we need to distribute across the top. So everything in the numerator, even that 2, to think of it 2 as 1, everything in the numerator is going to go together. The bottom's actually the easy part. If you notice, I have 2 x squared plus 3's right here, and I have 1 x squared plus 3 here. So I'm going to have x squared plus 3. I have 3 of them when I multiply them all together. The top is going to take a little more work, so I'm going to do it little piece by piece. So I'm going to have my 6x minus 2 from distributing here. Let me write that a little bit better. And then I need to have my 3 distributed here. So 3x squared plus 9 minus, distribute this 2x here, 6x squared. Distribute this 2 here, but also keep in mind that negative has to go through this as well. So I'm going to have positive 2x. Okay. So then now I can simplify that a little bit. So I'll keep my 6x minus 2. And then I'll combine my like terms in the top so that I have negative 3x squared plus 2x plus 9 all over x squared plus 3 cubed. The only thing you could do is if you wanted to distribute that 6x minus 2 through, it could be useful. Most of the time when we're using these things, we'll use them factored. So it's already kind of factored part of the way. So it would be most helpful to actually leave it like this in the long run. Oop. Okay, find the derivative. So, chain rule again, we just are introducing it with some trig functions to do it. So keep in mind the inside of this is 3x squared. So if I'm doing my y prime, it's going to be equal to the derivative of the outside, which is negative sine, keeping the inside the same, times the derivative of the inside, which is 6x. So I'll simplify that to be negative 6x sine 3x squared. If you want to put these parentheses there, I like those parentheses there. They don't always write them. Okay, there's that one. This one is interesting because cosine 3 looks like it's like an outside of your function, but it's actually a constant. So your derivative of this guy is just going to be 2 cosine 3. Cosine 3 is just a number. Okay, it's a little bitty number, but it's still a number. So cosine 3x. So essentially that's not really any different than having like 2x squared. It's just your number is cosine 3. So I think they tried to trick us with that one. All right. And then this one is a little different because you have multiple chains. All right. I have this very outside. And then inside that, I have this outside. And inside that, I have this. Okay. So we're going to do chain, chain, chain. So the derivative of the first outside is negative sign, keeping everything on the inside the same. Then this is my next inside that I need to derive and multiply by. So I'm going to have 2 times 3x times the derivative of that inside, which is just 3. So that I have, when I simplify, negative 3 times 3 times 2 is 18x sine of 3x quantity squared. Okay. You could have also just squared the 3x so that you would have had 9x squared, and you would still get negative 18x. So you can do that, but just keep in mind, chain of a chain of a chain, it's going to happen. All right, this one, it may help to rewrite it so that you have this quantity here, and you would have derivative of the outside, keep the inside the same. Now there's only one of them, times the derivative of the inside. And then you would technically derive x, which would just be 1. And you would need to simplify that, but really just that negative can go in front of that 2. In the order of the sine and cosine, you can change them around if you want. This one might help to rewrite as well. These are all y prime equals, not technically equal to the rewrite, y prime equals. This one I already rewrite to cosine x to the 1/2, not negative 1/2. I'm starting to derive it in my head. 1/2. So that when I do my first derivative, I get derivative of the outside, keep the inside the same. And then that exponent has to decrease. And then derivative of the inside, like this. So that I have, careful, the 2's on the bottom, the cosine x to the 1/2 power is on the bottom, but the negative sine x, it's in the top. All right. So reminder here, the derivative of e to the x is just e to the x, but this is my inside. So when you do your derivative here, it seems a little silly, but the derivative of the outside, which happens to be the e part of the function, is just e, keep the inside the same, times the derivative of the inside, which would be the exponent in that case. So if your variable's in the exponent, that would be considered being inside the function, where normally we have parentheses to help us notify the inside. We don't here, and you would rewrite that as 3e to the 3x. These take a lot of practice to kind of get used to identifying inside and outside. All right, so we're going to do something new. We're going to do derivative of natural logarithmic function. All right, so we have ln x. And the derivative of natural log of x is just 1 over x. So that's this. And this is what I remember the most, is this, because I can chain rule it. This is saying if you have a function u as a function, so think u as f of x, you could literally change that to f of x if you wanted to. It's just written out the chain rule for you. So it's the derivative of the outside, 1 over that function, times the derivative of that function. Du over dx would be the derivative of that function. Or they rewrote it as the derivative of the function over u. So I kind of like to think of it, if I had natural log, I can write correctly, if I had natural log of a function f of x, if I'm doing the chain rule full out, I would have 1 over f of x times the derivative of f of x, or an easier way to write it would be the first derivative over the original function. That is the chain rule worked out for you. You don't have to think of it that way. You can just think of it as chain rule. So we're going to practice it. So I have the derivative of natural log of 2x. Okay, that will be equal to my inside function. The derivative of natural log is 1 over whatever's inside of it. So that's the derivative of the outside times the derivative of the inside. So I get 1 over x. Okay. You could have just done 2 over 2x as well if you wanted to, and that would be okay. So this one, it'll be your inside function on the bottom and the derivative of your inside function on top. And that's not going to simplify. That's going to stay just like that. Or you could have done 1 over x squared plus 1 times 2x, and that's more of the chain rule type of thinking instead of just thinking of a new rule. It's the same rule we've been doing. This one's a product rule. It's telling us that d over dx is an operation. It's telling you to take the derivative of this. So I'm going to, there's my 1, there's my 2. So I'm going to do 1 d2, the derivative of natural log of x is 1 over x, plus 2 d1, which is just 1, natural log of x times 1. If I simplify that, I get x times 1 over x is just 1, plus natural log of x. Circle all my answers. Okay, this one is a bigger chain rule, derivative of the outside times the derivative of the inside. Okay, so there's the derivative of the outside, 3 comes down, power decreases by 1, inside stays the same, and the derivative of times derivative of the inside is just 1 over x because the derivative of natural log is 1 over x. And the only real way to simplify that is to just put them as one single fraction. All right, we are going to differentiate these functions here. All right, I do think this one is probably useful to rewrite it as this. You don't have to do that. It just might remind you. So this will dy over dx. This will chain rule. So the natural log is the first outside function that we have. And so I will have 1 over x plus 1 to the 1/2. And then inside, because it's actually this, if you're thinking about it, that whole thing is in the natural log, then I would have to chain rule the inside, so 1/2 x plus 1 to negative 1/2. Technically, times the derivative of the inside would just be times 1. You don't have to write that, though. And that is going to be equal to, when I simplify it, 1 over, if you notice, all the numerators are 1 when we multiply them together. And this part has to go down below because it's negative exponent. So I'm going to have x plus 1 to the 1/2 times x plus 1 to the 1/2. So I have x plus 1 to the add my exponents, which is just 1. You look at it, it looks psycho because you have what would be a chain rule on the top, and you have a chain rule on the bottom, you have a product rule on the top, you have a quotient, the whole thing. But instead of doing all that craziness, we can actually make it a little simpler by using our log rules. And so I can actually write this as the natural log of x plus the natural log of x squared plus 1. This is review from Algebra 2 pre-calculus and the beginning of our calculus stuff that we did in Chapter P, minus the natural log of the denominator. And you can take those exponents down if you want. I think it'd be easier because then you don't have to chain rule. So I have natural log of x plus 2 natural log of x squared plus 1. And you could have probably done that in one step, minus 1/2 natural log of 2x cubed minus 1. All right, so then we don't have as much chain rule. We're not going to chain rule. So when I do this derivative, f prime of x, derivative of the first term, natural log of x, is just 1 over x. The derivative of the second term is going to be plus the derivative of the outside, which is 1 over the function, times the derivative of the inside. And then we have minus 1/2, and the derivative of natural logs, constant, you're just multiplying by constant, so you can just leave it as a constant. Oh, likewise, I left off my 2 at the beginning of that, as I say that. Minus 1/2, derivative of natural log is 1 over 2x cubed minus 1, times the derivative of the inside, which is 6x squared. So we have this. Okay, we can simplify that quite a bit, so that I have 1 over x, and then I have positive 4x over x squared plus 1, and I have negative 6x squared all over. Actually, instead of doing that negative 6x squared, let's go ahead and simplify a little bit before then. You have a 6 on top and a 2 multiplied on bottom because of that 1/2. So like this term and this term can simplify so that you have minus 3x squared all over 2x cubed minus 1. And unless you were asked to solve this, like finding where it's equal to 0, where it's undefined, you can leave your derivative like that if you'd like. Otherwise, you have to get a common denominator, which means they would all need to be multiplied together. Okay, what if I do things that are not just with e? So when I have log base a or a base of a, so it's not e to the third power or x, it's 5 to the x. So kind of picture that here. If this were 5 to the x, I would have natural log of 5, the derivative of natural of 5 to the x would be natural log of 5 times 5 to the x. So it still stays the same, but you're going to do natural log that base every time. So like 2 to the x would be natural log of 2 times 2 to the x. So kind of like the e to the x would still be there. You could technically still do that. Natural e to the x derivative, the reason it's just e to the x is because it's natural log of e times e to the x, and natural log of e is just 1. So you don't have to write that part. Okay. I kind of ignore these for right now. Those are just the chain rule. And so it's kind of confusing when they write the rule out like that. If you would like me to explain that to you at some point, I can, but I think it's easier just keep your rule instead of having so much to memorize. If you just know the rule and then you know the basics, you can combine them and get those. And then if I had, instead of having natural log, if I had log base 10 or log base 5 or just log, which is log base 10, you would do 1 over natural log of that base times whatever's inside. And you would chain rule it if you had to. Okay, so we'll practice a couple of those. All right, so we are going to derive, that is 2 to the x. It's kind of blurry, but it is. It's 2 to the x. And so we're going to derive just 2 to the x. And so what the rule says, it's natural log of your base times exactly what it was before, unless you had to chain rule it. So if that numerator or that exponent was something other than just x, you would have to chain rule it. But the derivative of x is just 1. So then you can just leave it like that. Okay. So like this one, I would do natural log of my base. You're always going to do that. Times what it exactly is, but I have to chain rule that. So that's the derivative of the outside. That whole thing is the derivative of the outside. Times the derivative of the inside. So you'll just put a 3 here. You should rewrite that. It would be proper to write it 3 natural log of 2 times 2 to the 3x. Okay, so that your constants are all together. 3 is a constant, natural log of 2 is a constant. Okay, this one, if you look back at your rule for logs, it's 1 over natural log of your base. So when I do this derivative, I'm going to do 1 over natural log of my base times whatever is inside my function, cosine of x. So it's not unlike when you did natural log of x, you had 1 over x. Well, it's natural log of your base times everything, okay? And then I have to chain rule it, though. So the derivative of cosine is negative sine x. So I'll have negative sine x all over natural log of 10 cosine of x. Oh, this one's big. I would probably rewrite this. Sometimes that's the easier thing to do. Sometimes it's not. Sometimes it's just trial and error. If you're having a hard time getting somewhere, just start over and do something another way. Recommendation is to not ever get rid of what you've done. So if you mess up big time, you might take a picture of it on your phone if you're doing it on like Cami, so that you can have it just in case you were headed the right direction. You just didn't realize it. So I'll rewrite this though as log base 3 of x, but instead of doing root x, I'll put that exponent outside of it. So that's the numerator rewritten, divided by log of x plus 5. So we're using those log concepts for rewriting it. All right, so then for each one, I will have 1 over, for the derivative, dy over dx. I will have 1 over natural log of my base, in this case 3, and I keep the inside the same, and I can't forget that 1/2, so I'll just stick the 2 in the bottom. It's still there, times the derivative of the inside, which doesn't really bother anything, minus 1 over natural log of my base times what I have on the inside, and I would technically need to derive x plus 5, but the derivative of x plus 5 is just 1. I do think this would look better if we got a common denominator. So if we do that, they're just going to need each other essentially. So the denominator is going to be 2 natural log of 3. I don't necessarily need that to go twice. the left one has an x and the right one has an x plus 5. So we just took from everything that they all had so that we each have it all. Okay, so then the numerator on the left is going to be natural log of 3 x plus 5. And the numerator on the right is going to be 2 natural log, I lie. We didn't need those natural logs. They already had it. Take off the natural log. Take off the natural log. So it'll be x plus 5. Where's my marker? So we have 2 x plus 5 minus 2x. There we go. So the right side, let me just write that out so we have everything. This side, I needed to multiply top and bottom by the 2 and the x. This side, I need to multiply top and bottom by the x plus 5 as a whole. Both top and bottom had to have that. Okay, and so that left me with this. And if I simplify that, it's not too bad. And I will get 5 minus x all over. The bottom is actually the ugly part. We were able to simplify the top. So we have 2 natural log of 3x times x plus 5. If you want to distribute the x and the x plus 5, you could. Just make sure they stay in parentheses. So that is that big thing. Last thing is on in your textbook, page 167. I'm not going to go over all this. This is all of the rules we've learned up to this point on one page in one table, which is useful. So if you were going to make note cards to memorize this stuff and you need to memorize this stuff, you could use these. Or you could write the rules in your own words, kind of like we did with some of the other rules, and that would be okay. But I just wanted you to have an idea of where that was because it can be very helpful.